Hello, I'm Andrea Malchiodi, the current director of the Geordie Mathematical Research Center. I would like to welcome you to the summer school on recent perspective on Hodge Theory. And I will just say a few words, and which will take only a couple of minutes. So the Geordie Center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, with the aim of becoming like a meeting point for the whole mathematical community in Pisa, including people from Scuola Normale, the University of Pisa, and also some small community from Scuola Superiore Sant'Anna. These other institutions also contribute financially and crucially to the activities of the center. So the main activities since the foundations have been workshops, schools, and intensive research periods. And we also recently resumed with a colloquium series. We have visiting positions of two types. So there are 2 years postdoctoral positions, and also there is opportunity to perform a research in pairs for a visit for a short time. As many centers of this type were strongly affected by the pandemic. But since the last fall, we resumed almost normally with the activities. So we will see how it will go the coming academic year. And I just want to conclude thanking the organizers for bringing up this event and the staff of the center for their constant and very valuable help. Okay, so welcome.
So thank you for being here, and it's a pleasure to start with Bruno Klingler. He's going to talk about Hodge theory between algebraicity and transcendence.
Thank you. So first of all, everybody hear me? Yeah, that's fine. So first of all, I would like to thank the organizers for inviting me here. Yeah, so I will talk about Hodge theory between algebraicity and transcendence. So I have only 4 hours. So basically, the goal is to introduce you to recent progress in Hodge theory, based on use of model theory, namely o-minimality, and also ideas from functional transcendence and atypical intersections. So this will be the 3 topics. So the plan of the lectures will be the following. So today, essentially, it will be an introduction. Because I'm the first lecturer, I will spend some time on basics on Hodge theory. Then tomorrow, I will talk about the relation between Hodge theory and tame geometry. Then I plan to talk about functional transcendence. And then in the 4th lecture, I will talk about atypical intersections in Hodge theory. So that's roughly the plan. And as I said, because I have only 4 hours, I apologize, but there will be very few proofs, actually. I mean, detailed proof. I will try to give some ideas, but it will never be very precise. All right. So as I said, I want to start by recalling a bit of Hodge theory. So if I'm too boring, you can just interrupt me if everybody knows what I'm talking about, so that I spare some time. OK, so Hodge theory in a nutshell. So there are various understandings of what Hodge theory is about. Maybe you heard a lot during undergrad and grad studies about harmonic forms and so on. I will not touch at all about that aspect. So what I want to understand is well, the relation with classical algebraic geometry. So basically, what is Hodge theory is just a linearization process for varieties defined over the complex numbers. So suppose you start with x over c, an algebraic variety. And then usually this is quite a complicated object to understand geometrically. So what you try to do, you try to linearize it. And by this, I mean, this is the standard procedure that tells you that you can consider its cohomology. So there are various cohomology theories. The first one is just to consider the set of complex points of that algebraic variety and just take the usual singular cohomology that I would call the Betti cohomology. So we get a finitely generated Z module which is a rather nice and simple object compared to that guy. And for what I'm interested in, there is a second object, which is the algebraic de Rham cohomology. So you consider algebraic differential forms. Okay, here you can assume that this is smooth to make things easier. So so you get those two theories, and this one is purely algebraic. So maybe I should recall what it is. So if you have x over c, and let's assume, for instance, that this is smooth, and actually I would also suppose this is projective, such that the theory is much easier. Then what is that guy? Well, basically, you can consider the de Rham complex of algebraic forms. And so on. So this is a complex of algebraic covariant sheaves, and you take the hypercohomology of that. Okay. So this is the hypercohomology of that de Rham complex. All right, so you look at this, you get this finitely generated Z module, and you get this purely algebraic object, which is a complex vector space of finite dimension. And basically, Hodge theory is a way of using this algebraic object to enrich the topological objects that you have. As you know, the Betti cohomology is a topological invariant. This means this is invariant under any, it's a homotopy invariant. So actually any topological space which is homotopy equivalent to X of C has the same guy. So this is very flexible. It's too flexible to get enough information about X. But what we want to do, we want to use that guy to enrich the structure there. And so the way you do it is that basically you will enrich that thing with a Hodge filtration. So a certain filtration on the complexified vector space. So now you get a filtered vector space. And the basic result in Hodge theory is that actually this filtration is not any filtration. This is what is called a Hodge structure. And moreover, it is polarized. So I will come back to the definition of this later. So at that point, you could consider you are done. Basically, you have replaced this algebraic variety with a Z module and a filtration on the complexified vector space that satisfies a lot of properties. And this is your Hodge structure. Okay, so that's the first point. But actually, I want to convince you that you shouldn't stop there, even if in classical books on Hodge theory, you stop there. Really, what you attach to that is an algebraic group. Defined over Q, which is called the Mumford group of X. So in a nutshell, Hodge theory is this process. You start with an algebraic variety over C, the complex numbers, and you get an algebraic group over Q. So this is a major simplification because algebraic groups are much easier to understand than general algebraic varieties. But the second thing is that there is some mystery, right? I mean, C is an uncountable field, but Q is countable. So the first thing it tells you is that this construction can certainly not be algebraic. Okay. So this construction is not algebraic. In other words, this means that if you give me a realization of X as solutions of a set of polynomial equations in the projective space, then usually there is no way I can give you the corresponding algebraic group from those equations. I just don't know how to do that. And maybe I want to give a very few examples. So you could argue that my argument about uncountability versus countability was a fake one. Suppose, for instance, that X is defined over Q, and then maybe there is a solution to define algebraically that group. And what I want to show you on that example is that, well, maybe, but you would have to be very smart to do it. So let's do this one. Consider the following set of equations. Y squared plus y is equal to x3 plus alpha, where alpha is in Q, for instance. So you take this into the affine space of dimension 2, and then you take the smooth completion. Take the smooth completion x alpha in P2C. And here you can take your parameter alpha being in Q if you want. So what I claim is that if you look at the group that we'll get for this x0 over Q, so in the case where alpha is equal to 0, then the group that you get is a torus that I can define as being the restriction of Q square root minus 3 of the multiplicative group. So for people who don't like algebraic group, in terms of matrices, it's just a set of following matrices. Let's try to write this properly. So this is a subgroup of 2 times 2 invertible matrices of the form mu u w minus 3w. Okay, and this is a restriction of scalar of the multiplicative group from this quadratic imaginary field q of square root minus 3 over q. Okay, so we get that one. And now, if you put alpha being non-zero sufficiently small, well, you get that that group is actually GL2Q. Okay. So for people asking themselves what happens, it happens that this parameterizes elliptic curves. So for alpha is equal to 0, you get an elliptic curve with complex multiplication by that imaginary quadratic field, and all the other ones are ordinary ones, and so you get GL2. Let me give you a second kind of example. So suppose I give myself a polynomial of on n plus 1 variable, which is homogeneous of degree d. Then I get a hypersurface in the projective space of dimension n. So here I should take alpha rational. Let's suppose for simplicity, and this is generic, that xf is smooth, so that I'm in the situation that I've been describing. Then if you choose d larger than, let's take n larger than 2 and d larger than 3, then in general, I'm completely unable to determine what is the group, depending on that polynomial. Okay. So don't know how to compute GXF. Okay, so this is strange, right? I mean, you are constructing a theory which is supposed to simplify your life, but actually you don't know how to compute it. But nevertheless, I want to convince you that as in many cases in mathematics, when you develop a theory, sometimes actually you are not able to compute, but nevertheless, it's a big improvement in your life. All right, so this was a rough introduction. So you have just to think that Hodge theory is a simplification of algebraic geometry over C. Now, of course, I have to come back to how to construct that group. So are there any questions? So no? Okay, so as I said, you start with your x over c, then you take the associated complex analytic variety xn, rather than writing x of c. I will really think of this as being an analytic manifold. So, and then you get this Betti cohomology. So this I will not recall. You take whatever topological cohomology theories are all equivalent. Take singular cohomology, simplicial, whatever. They are all the same. Or if you want, this is the sheaf cohomology of the constant sheaf Z on that space. Gives you the same thing. So as I said, this is a Z module of finite type. Okay, so how do you construct the Hodge filtration? Well, I told you how to define the de Rham, algebraic de Rham cohomology, which is, maybe, let me change the board. I need the entire board to do that. So you take this holomorphic de Rham complex. Of course, it is not a resolution of an acyclic resolution. So you have to take hypercohomology and so now how you do proceed? Well, here you want to relate this to the singular cohomology. So the first thing you use. So as I said, now I'm assuming everywhere X smooth projective for simplicity. So this means that in these lectures, I will talk only about pure Hodge structures, no mixed Hodge structures. It's technically more involved, so I don't want to spend time on this. So now I use a Serre-Gaga result. So I come closer to my space because now it's the same thing as the hypercohomology of the analytic de Rham complex. Okay. Now that guy is really quasi-isomorphic with the constant sheaf C, and so this means that that thing is actually isomorphic. So this is my canonical isomorphism with the singular cohomology. Good. So now, as I said, I want to define the filtration here, which will be my Hodge filtration. So this will be filtration by a complex vector space of this finite dimensional complex vector space. And the way I do it is, in some sense, completely trivial. I just truncate that complex. So what I do is inside this complex, I just keep the piece of only in size larger than P. I take the hypercohomology. So, so this is a subcomplex of that complex. So there is a natural map. Now it happens that this map is actually injective, so that makes my life easier. But a priori, I could just take the image of that space, but this is injective. And actually, this is my Hodge filtration. I follow this chain of isomorphism there, and this defines my Hodge filtration. So if I present it this way, you see that the Hodge filtration really comes from the algebraic structure. Okay. So that's the basic construction. And so now, if you look at this diagram, you see that really Hodge theory is about the interaction of this filtration, which is defined algebraically depending on the coefficient of X, and the rational or integral structure coming from the singular cohomology. So this is why, in some sense, there is some number theory hidden there. And this is what we want to understand. In particular, it's very natural from that point of view to say that the most important objects in Hodge theory are the Hodge classes, which really incarnate the interaction of the filtration with the integrality properties. So what are the Hodge classes? Well, these are the Hodge classes, which are exactly in the right, the integral classes, which are exactly in the right place in the filtration. So this is FP intersected with H2P, B, X, and Q. So I think of this intersection inside H2P. X and C. Okay. So, and so I was saying that Hodge theory about this interaction of this algebraic filtration and the rational structure. So this is really incarnated here. And classical cycle theory tells you that you are really doing the right thing, because now suppose you consider algebraic cycles in X of codimension P with coefficient Q, then you have a cycle map just taking the cohomology class of that thing, and the basic result is that you lie in the Hodge classes. Okay. So up to now, I'm kind of happy. I've enriched a bit the structure. I have a finitely generated Z module, and I have a filtration coming from the algebraic structure and the complexification. Now, what is much more important actually to get really started is the following theorem, which is due in various generality to Hodge, Fröhlicher, and then in the general case by Deligne. That tells you that actually you get more than a simple filtration. You get what is called a Z-polarized Hodge structure. So what is this? Well, you get a triple, which is this finitely generated Z module. Then the Hodge, up to now it's just a, I'm not including the polarization, so it's just a pair. So this pair is polarizable. The Hodge structure, I just write the HS of weight I. So what does it mean? This means that actually, and this is crucial, as I will explain in 1 second, is that actually you have the following decomposition. When you tensor, when you look at your complex vector space, then this filtration actually defines a bigraduation. This means that this is actually equal to Fp plus Fi plus 1 minus P bar. So here already you see something strange. The real structure given by the Z module comes into the picture, right? You get this decomposition where here you have the bar, which is just a complex conjugation with regard to that real structure. And this is equivalent to saying that actually you get a bifiltration, bigraduation. So that guy is equal to you get such a decomposition, and VPQ bar is equal to VQP. So how do you pass from one to the other? Well, VPQ is FP intersected with FQ bar. So it tells you that actually the filtration that I have defines graduation. So this is the notion of the Hodge structure. And now the polarization condition is a pain to write, but actually, as you will see in the further lecture, it's an absolutely crucial point. It tells you that this bigraduation, moreover, there exist bilinear forms that has very strong positivity property with respect to this bigraduation. So the second condition on polarizability is that there exists Q, which is a Z bilinear pairing which is -1 to the I symmetric. So this is symmetric if I is even and anti-symmetric if I is odd, which satisfies two conditions. The first one is the following orthogonality condition. So if you complexify this pairing, then it makes Fp and Fi plus 1 minus P orthogonal. And now QC evaluated to a class V and a class V bar. Well, it's not definite positive, but if you modify it this way, then it is positive definite, where C is equal to I to the power Q minus P on VPQ. So the VPQs are orthogonal, and moreover, they satisfy this positivity property. So these are what are called the Hodge-Riemann relations. So if you had the opportunity, I suggest that you look at the plenary lecture by Junehu in the last ICM. He made a very nice lecture. So he's not interested in algebraic geometry, actually, but he's really interested in those relations, how Hodge structures appear in purely combinatorial phenomena. And yeah, you can have a look at this. It's very nice. So why is that important? Well, from an abstract point of view, the first point tells you that you replace the filtration by a graduation. Why is that important? This is important because the category of filtered vector space is a bad one, right? It's not a billion. But the category of bigraded vector spaces is. So you get an abelian category, okay? So, so one tells you that the category of the Hodge structure is an abelian category. Okay, I did not define what are the morphisms. The morphisms are the obvious morphisms. So it's a morphism of Z module, such that when you extend to C, then you map filtration to filtration. Okay. So this is an abelian category. And actually, it's even more than that. The second one tells you that, well, this relation tells you that actually it's Tanakian. So in fact, any bigraduation is given by a representation of C star cross C star. But here, because of this conjugation relation, it's just a representation of C star seen as a real algebraic group. So in fact, this data of the real vector space with such bigraduation, so R Hodge structure, is the same thing as a representation from C star, which is the restriction of scalar from C to R of the multiplicative group to GL VR. So if you think it this way, it becomes obvious that the category, at least of R Hodge structure, is abelian, because this is a category of representation of that group, and this is a Tanakian category with Tanaka group, that torus. Okay, and the relation is just that, okay, if you take Z in C star, it acts, well, there is some convention here, but my convention, it acts by Z minus P, Z bar minus Q on VPQ. Right, so here I'm just saying that if you have an abstract bigraded vector space, it's the same thing as a representation of C star cross C star, where the first C star acts by Z minus P on for the piece of VP, and the second by Z minus Q. And here, this conjugation relation tells you that actually this is really a representation of that group. So please don't think that this is abstract nonsense. This is absolutely crucial for what follows, because this is the way we will define the Mumford group. Questions about that? Yeah. No, actually, because I'm writing just polarizable. So polarizable means that you're right that what is canonical is the polarization on the primitive part, but okay, I can decompose the cohomology in primitive plus orthogonal complement and then put a polarization there. So I'm not working with the category of polarized, but really polarizable. Yes, you're right. Yeah, of course, you see that the torsion in the Z module is killed, right? Because I'm mapping to Z, so. Yes. Yes. Thanks. And we'll see that the second condition, so forget about the orthogonalities, is very useful, of course, but what I want to emphasize is that this relates Hodge theory really to quadratic forms, and we'll see later that it really plays a crucial role, this positive constraint on the filtration. Okay, so now I'm almost done. So now you know what is a Hodge structure. So of course, I'm not giving the proof of that theorem now, but I will come back in 1 second to that. Okay, so where are we? So now we started with this X over C. Now we constructed this Hodge structure, a polarizable one, which is maybe I won't even write the polarization now. Maybe I will write the Q, at least it exists. So this is a polarizable the Hodge structure. And now I claim that associated to that, I want to get a group of a Q. Which will be actually the group associated to that polarizable Hodge structure. So what is the definition of that group? Well, if you start with any Q Hodge structure, even, you can forget about the Z here. It's not so important for what follows. What is GV? Well, this is the Tanaka group. So I told you that the category of a Q Hodge structure is Tanakian. And so, of course, the Tanaka group of that category is very complicated. It's a pro-algebraic group. But what you do is that you restrict yourself to a small subcategory of that category, which is a category of Hodge structures generated in a tensor sense by V. So this means that you take the smallest tensor subcategory there. So this means that this category is generated by all tensor powers of V of its dual, and then you take all subquotients. Okay. So so this is the first abstract definition. This is your Mumford-Tate group. A more readable maybe definition is to use this interpretation in terms of representation of age. Too bad I already erased. Okay, let me first give maybe the intuitive one. This is the fixator of all Hodge classes, not in V, but in V tensor A cross V dual tensor B, and then you take the sum over all AB in N. And here I should be a bit more careful because I was not very careful. I define the Hodge classes as being FP intersected with H2P. Here, what I want to do is just take Hodge classes of weight 0. So from now on, what I will call Hodge classes are really Hodge classes of weight 0. So you don't know what what the weight of V is, but if you take big tensors powers like this, anyway, it's clear that you will get a lot of things of weight 0. And then you can look at Hodge classes there. And this is what I want to look at. Okay, so here it should be of weight 0. So you are looking at F0 intersected with the rational structure there. Okay. Yeah. So this is maybe a more down to earth definition. But actually, the convenient one is the one by Deligne. You add this morphism from C star to GLV. And what you do is you take the image of that group. So when I say fixator, this is, of course, in GLVQ. So what you do is you take the image of that group. So this is inside GLVC. And now you take the Zariski closure of a Q. So you take the smallest algebraic group defined over Q, such that when you extend the scalar to R, then it contains the image of that group. Okay. So exercise proves that those three definitions are actually the same. Are there any questions? So if you summarize, you have the feeling that maybe some things are algebraic. So this is true that the filtration is algebraic, but you see that there is a crucial appearance of the complex conjugation here. And this is not algebraic. Okay. And when you do the classical theory, usually what you do is that you will represent classes in VPQ by harmonic forms of type PQ. And those harmonic forms, clearly, they are not defined algebraically. But they are not so far. Yeah. Yes. Yes. Yeah, it's a pure Tannican formalism there. All right, so yeah, it was a fast crash course on Hodge theory. So now what I want to do is I do not want to solve the Hodge conjecture. I want to solve the variational one. No, I'm kidding. But I want to do it in families. Okay, so what will be important in what follows is that it's always the same story in mathematics. It's usually very difficult to say something on one object, but if you have a family of objects, then studying the variations are usually much easier. So this is what we want to do now. So now let me move to this same story, but in family. All right, so suppose now that I have a family of smooth projective varieties. This means I have a smooth projective morphism of a C, and S is supposed to be quasi-projective and smooth. And now I just glue everything I did before as a family of a S. So I get what is called, in the same way as from X, I got a polarizable Hodge structure. Now, from that family, I call what is called, I get what is called a polarizable Z variation of Hodge structure, ZVHS. So what is this gadget? So I will replace this very complicated morphism by the following gadget. So first, I put together the Betti homology. So I get a local system because the morphism is smooth and projective. So this is the collection of the Betti homology of the fibers when S varies in the base. Then I get the corresponding algebraic de Rham homology in families. So this is an algebraic vector bundle over S. So I get this V. Let me call this curved V. So this is a collection of algebraic de Rham homology. And now I have the Hodge filtration on each of those fibers, and it will glue together because this is algebraic. It will glue together to give me a Hodge filtration on this thing. So I should say this is the local system on Sn, and this is a filtered algebraic vector bundle on S. And then, because I have this Z local system, when I complexify, I get a flat connection, nabla. And actually, this flat connection will come from this algebraic vector bundle. So this will be the flat algebraic connection on V. And then I have the polarization, which is a morphism from the Z local system to the constant local system on S. Or maybe here I should put a double bar. This is really a local system. So this is this gadget, but you understand that I just did nothing. I just put them together, what I did on each fiber. So of course, what is the relation? The relation is that, so I have this algebraic vector bundle under the Riemann-Hilbert correspondence. It gives me the complexified local system associated to that guy. Okay. So now, what are the compatibilities? And this is where first miracle occur. So what are the conditions? Well, and the most important miracle is the first one. The first one is that, so what happens when I apply? So first I should say, actually, let me write that when I identify that guy. So now this is a complex holomorphic vector bundle with a complex analytic flat connection. Then under the Riemann-Hilbert correspondence, this is really this local system tensor by C. I already said it. I want to have polarizable the Hodge structure on each fiber. So coming from the Hodge theory, but what is the miracle? The miracle is what is the relation between the flat connection and the filtration? Okay. So I have my flat algebraic connection. I can apply it to a vector which is in some piece of the filtration and ask what happens. And then the constraint, which is called Griffith's transversality, is that actually, of course, the filtration will not be preserved. It's not flat. It's not a filtration by flat algebraic vector bundles, but it satisfies that the filtration is shifted at most by 1. So recall this is the decreasing filtration. So Fp minus 1 is a bit bigger than Fp. But what I know is that I'm not moving the filtration too much, just at most by 1. Okay. So this is called Griffith's transversality, and this is absolutely crucial everywhere. So it was proven by Griffith in the 60s. So actually, if you think about it, this tells you that, abstractly speaking, this guy V with the filtration and the flat connection, this is a filtered D module. Okay. So that's it. This is the theory, the variational theory. Good. So it looks very heavy. And now what I want to explain is a much more geometric interpretation of this picture. Right, this is kind of heavy because I have this local system, I have the algebraic vector bundle, I have to go from one to the other, and so on and so forth. But now let me give a purely complex analytic map description of that thing. So, and this is called period maps. And I should emphasize that this is what makes the crucial difference between Hodge theory and, for instance, if you are working with L-adic cohomology. L-adic cohomology is very nice, but there is no such filtration, and so this means that there is no period map. And as we will see, everything we'll do later for variational Hodge theory comes from the period map and actually comes from this Griffith's transversality. Okay. So what is a period map? Well, after all, what you want to describe the Hodge filtration on a local system. So the first thing you do is you trivialize the local system, which means you go to the universal cover. So your local system becomes trivial. And this means that now you just have to describe a filtration on the fibers, but all fibers are now the same. So basically, you just have to describe the possible filtrations appearing on one given finite dimensional complex vector space. Okay, so in symbol, this means that you look at your base, you as a complex analytic space, take the universal cover. Now here you add this Vn, analytic vector bundle. Then you put it back to the universal cover. But now, because this is a flat vector bundle, it's canonically trivialized. So it becomes equal to Sn tensor a certain fiber that I just denote by Vc. Okay. And now inside this, I have my filtration. When I pull back, or if you want the pullback of the filtration here. Okay. So now what I want to write is once I am on the universal cover, it's much easier, right? I just have to define at each point in the universal cover what is the filtration of VC that I get. So let's do that. Well, I just look at the space of all possible filtration. So, well, you can look at the flag variety of VC corresponding to the dimension of the flag, which is a constant on my space. Okay, so that's one thing. So this is some GLNC modulo some parabolic. I'm just parameterizing all possible flags of a given type. So I will get a map from the universal cover, which will attach to a point here, the filtration on VC that I get. So now the point is that actually I will lie in a smaller domain, which will be also a flag variety, but for the generic Mumford-Tate group of a generic fiber. So actually, it will be G of C modulo some parabolic that I will denote by P, where what is G of C? G over Q will be the Mumford-Tate group of a very general fiber. Right, when I have my variation of Hodge structures, at each point I have of the base, I have a Hodge structure, so I have an algebraic group over Q. Now the claim is that this group is locally constant outside of a meager set on Sn. So I take a point outside of that meager set, and I trivialize the Mumford-Tate group on the universal cover. I get an algebraic group over Q, and this is that group, the generic Mumford-Tate group. So this would be called the generic Mumford-Tate of the variation. And what I'm claiming is that actually inside this flag variety, I'm just living inside one orbit of this generic Mumford-Tate group, which is also a flag variety for this complex group. Now, there is one more point. I did not use the polarization yet. So not only I will lie inside an orbit of the complex points, but what I claim is that I lie inside an orbit of the real points. So I will lie inside D, which is D of R, modulo some group that I would call M. And now, actually, it's easy to see that this is open in the analytic sense. Yeah. So you are in the situation from the algebraic point of view theory where you have a flag variety and you are looking at an open G of R orbit inside it. Why is that open? Well, if you remember the positivity conditions, this was just a semi-algebraic positivity condition. So this is certainly open if it's not empty. All right. So it already tells you that those groups are very special because it's not true that any group, algebraic group of a Q, satisfies that property, that there exists a G of R open orbit. All right. So this is the picture. Let me repeat it here. So is it clear, this picture? Because this is absolutely crucial. You just parameterize the flags that you get on the universal cover, and the claim is that coming from all these restrictions that I had on the possible filtration, actually I live here. So I will give examples in 1 second, but okay, so now let's complete the diagram. So I have this map at the end of the day. And now I want to descend to my original space S. Well, now you remember that I started with the Z variation of Hodge structure, which means that the monomy lies in G of Z. And now it happens that that group is compact. So the monomy acts properly discontinuously on that space. And so this means that there is a complex analytic manifold. So gamma will be G of Z, basically, such that you have such a diagram. And this is what is called the period map. Okay. Now the claim is that giving yourself a variation of a structure or giving yourself such a period map, it's an equivalence. So, but I have to describe precisely what are the constraints on such maps. It's not any map because there is still something missing. And what is missing is Griffith's transversality in this picture. So the first remark is that here everything is analytic. I go to the universal cover, which of course does not exist in the algebraic category. I have to go to the complex analytic space, and so on and so forth. So this map a priori is purely analytic. So phi, so d mod gamma is complex analytic. Phi is C analytic. And now I want to use a Griffith's transversality. The claim is that phi is severely constrained. It has to satisfy some differential equations. And those differential equations come from the existence of Griffith's transversality. So what is the constraint? The constraint is that the differential of phi, it has to lie in a very precise subbundle of the holomorphic tangent bundle on d mod gamma, which is called the horizontal tangent bundle. And this is equivalent to Griffith's transversality. So now let me describe this bundle for you. Well, I will use group theory. So if you are not confident in this, I can explain in more detail if you ask me questions, but maybe later. So yes, this group M here. So G of Z is a lattice in that group. Okay, so this means that it acts properly discontinuously on G of R. But when I take the quotient by a compact group, it's still properly discontinuous. Okay, so this quotient exists in the analytic category. So if you prefer, for you, this is an elliptic orbit. All right, so well, you should know a little bit about the theory of tangent spaces to flag varieties. But basically, this is a G of C homogeneous space. So the tangent bundle can be written as GC cross, well, you take the Lie algebra, and then you take the quotient by the Lie algebra of the corresponding parabolic. And this is over P and for the adjoint representation. Okay. But now what I'm saying is that actually GC as a Hodge structure at each point. So if you want to run this as GC cross P add F minus infinity. So at each point, G is a representation of your Mumford group. So it's automatically a Hodge structure. And so of weight 0, actually. And so what you are really writing is the entire space modulo the F0, because the stabilizer of a given Hodge structure is F0 in the endomorphism. So you get this. And what is the horizontal tangent bundle? Well, this is just the F minus 1. So a very small piece, just the next step. And the constraint is that your tangent map has to lie in this very small subbundle of the full bundle. So if you prefer, and everything is G equivalent to, so it restricts to D and then it descends to D mod gamma. Okay. So you have to think that in this flag variety, you have this totally non-integrable distribution. This is the contrary, this is at the opposite of what a foliation would be. It's really non-integrable. And you construct an analytic submanifold, which at each point is tangent to it. So it really tells you that it's extremely constrained. Okay. So now remember that the most important thing for a single Hodge structure were Hodge classes. So now I want to consider the Hodge classes, but in family, and this will be the notion of Hodge loci. So what is a Hodge locus for this Z variation of Hodge structure? So this will be a subset of the base. A priori, it's just a set. So this is a collection of points in the base such that if you look at this Hodge structure, it has more Hodge tensors than the very general fiber. And it's exceptional Hodge tensors. And if you prefer, in terms of the Mumford group, you look at the Mumford group at the point S, and you ask, of course, it will be contained in the direct Mumford group that I denote as G big S, but it is strictly contained in it, right? If you have more Hodge classes, the Tanaka group becomes smaller. And this is a mega set. So the first result of the line is that this is a mega set. Of this analytic set. Now, what is important for us is to understand this locus in terms of the period map. So I have my period map phi going to D mod gamma. So if I have a smaller Mumford group, I can construct a lot of smaller domain inside D mod gamma. They will be of the form D prime mod gamma prime. And there will be a countable union of such guys coming from all possible morphism of Q algebraic groups of the form G prime and then the auxiliary datum D prime inside GD and strictly contained. Well, okay, I will, in some sense, forget about Mega. It's not important because I will state a much stronger theorem in 1 second. Okay, I don't want to. Oh, I thought you knew by heart all the Bourbaki volumes, whatever. Well, the one in on topology are not the best one, maybe, but anyway. And so you look at that map. So if you have a smaller Mumford group, this means that you lie in one such collection, one of such guys. And so the Hodge locus is actually just given by this product here. So this is the sublocus of Sn that lies here. So the picture is very simple. You have your S. You are mapping to D mod gamma. Let me very round. And in D mod gamma, you have very special collections of possible different dimensions of such guys. But this is countable. What is important here is that this is countable because those data are defined over Q. So you have a countable collection of space of the same type, but of smaller dimension inside there. And then your Hodge locus will be the pre-image. So you will map this here and it will lie somewhere and cutting those spaces. Okay. So the Hodge locus will be the preimage there, and you will get a countable collection of things, which are analytic because phi is analytic. So let me give some examples, maybe. Yeah, I'm very late, of course. So let me start with a trivial example. So one of the simplest example is take for X an elliptic curve, but then I will just consider them in family. So my family will be the universal elliptic curve. So S will be the moduli of elliptic curves. Okay, I have to put some level structure so that this really makes sense. And this is the universal elliptic curve. Okay, so now I want to understand the previous picture there. So what is the universal cover of that thing? Well, basically, this is a collection of all elliptic curves, but where I fix the basis of the homology. So E elliptic curve over C plus trivialization of the homology. Let's call two generators as being gamma 1 and gamma 2. Okay, so this is this. Now, what is my period map at the level of the universal cover? Well, what do I want to consider? The local systems that I'm considering is the first cohomology of the fibers. So this V is really R1 F lower star Z, VZ. Okay. The elliptic curve will be completely described by its first cohomology. So this first cohomology is a two-dimensional vector space. And now I want to parameterize filtration of a two-dimensional complex vector space. So this is exactly P1. So I know that I will lie in P1C. Actually, the Generic-Manforte group in that case will be GL2. So in this picture, where is it? It disappeared already. It was here. GC is already GLVC. So there is no difference here. Now there is this D, which is the open G-orbit. And here, the positivity condition tells me that I will lie in the union of the upper and lower half space inside P1C. And what is the map? Well, the map is easy. If I have such a curve E, it is mapped to just the periods. You know, on an elliptic curve, there is basically up to multiplication a single holomorphic one form. So what you can do is you take the couple of periods and you take the quotient of them. And actually, this completely describes your filtration. And the positivity condition is that this ratio actually lies here. It cannot be a real number. And so now what is the map here? Well, you go to H plus minus modulo GL2Z, which is the same thing as H plus modulo SL2Z. So you get the usual modular curve. And in this case, which was observed by Riemann a long time ago, now I want to convince you that Hodge theory is useful. In this case, this morphism is actually an isomorphism. And notice that in this case, there is no transversality condition because in some sense, this space is just too small. Okay, it's just the tangent space is one-dimensional. It is equal to the horizontal tangent space. So you don't see the transversality condition. And Riemann tells you that there is an inverse to this, and this inverse is a famous J function. Okay, so, and it tells you that this guy is actually just C. Okay, there are some orbifold phenomena that I'm passing under the carpet, but we don't care. So now on this picture, the Generic-Manforte group is GL2, so GS is GL2Q. Okay. Now, if we come to that point, I should have defined I. Yes, here. Ah, there is no color. Okay. Ah, there is. here I want to define the crucial invariant, because you see that this is what will play a role with respect to Griffith's transversality. This crucial invariant will be the length of the Hodge filtration on this Lie algebra. So what I will call the level of V, which is in some sense a measure of the complexity of the variation of a structure, will be the max of the L such that G minus LL is different from 0. So in this case, the level is 1. So this is why this is trivial in some sense. So maybe I should even make a picture in terms of matrices. Right? If you think of the Lie algebra of the Jering-Forte group and you complexified it, so these are just 2 times 2 matrices, right? So what is the F minus 1? Well, the G minus 1, 1 will be the upper, I mean, it will be 0, 0, this. So G0, 0. Well, maybe I put star, it's more readable. It will be this. And the G11 will be this. Well, depending on your convention, the filtration, but okay. So now, what is the Hodge locus in that case? Ooh, I'm already late. Can I take 5 more minutes? Is that okay? Thanks. So the Hodge locus in that case are exactly the points in this moduli of curves where you lie in the Hodge locus in P1C. Now P1C is one-dimensional, so you see that the subvarieties d prime mod gamma prime have to be points there. Okay, and this is exactly what happens. So the Hodge locus of S is a collection of J of tau, where tau is imaginary quadratic. In H. So the subspace of the form d prime mod gamma primes are exactly the points corresponding to tau imaginary quadratic there. And an important remark is that because there is transcendence and algebraicity in the title, is that this is contained in Q bar inside C, which is Sn. Okay. And another remark is that this Hodge locus is actually dense, even for the usual topology here. Okay. It's too bad. I'm half of what I planned. I guess I have to stop here, otherwise I would just, yeah. So I stop here. Yes. This is recorded, so you need a mic.
Yeah, it's a question about the terminology of period maps. So in your example, we see, well, like why these are periods of elliptic curves. In general, is it known, or if it's like general, it gives it, the period map is given by periods of algebraic cycles?
So you see that actually it's a bit more, it's not exactly periods, it's ratio of periods. So it's a subtle point. If you were really looking at periods, you would be looking at the full vector bundle over that space, but you are essentially correct. So in general, this is the same picture. To describe FP, what you have to take? Well, you have to take a form of type P and then integrate over corresponding integral cycles. So it's also given by ratio of periods, but of course this is more complicated because now you see that those differential forms which were canonical in the case of elliptic curves, in general, they're absolutely not canonical. So, okay. But it's still generated by those things.
Thank you.
Thank you. Just so I I'm sure I understand the final example. So you have all the imaginary quadratic points corresponding to complex multiplication,
Yes.
and you're saying that those are
Yeah, so I was going fast. So what I'm saying is that here in H plus, I take all the imaginary quadratic points, I project them to this quotient. This become dense. I mean, this is dense, obviously, for the usual topology because it was already dense in H plus, actually. And then by this map J, I lie inside C, and so these are the J value at those points are the complex multiplication points here. Okay, and what I'm saying is that what is remarkable is that if you start from such a tau, which is imaginary quadratic, then J of tau is actually in Q bar. Okay, so you see that there is an interplay because those guys are well, I can already explain what we'll see in 2 lectures. You see that those points, they correspond to things which are algebraic at the level of the universal cover, at least in the period domain, and they're also algebraic here. And actually, these are the only bi-algebraic guys.
And one other question, just briefly. So you made a comment that the polarization on the primitive part is somehow canonical, and I didn't understand that. It was a quick comment, but.
Well, just because this is given by intersection theory on the primitive cohomology. So if you fix the polarization on, you fix an ample line bundle on your algebraic variety, so you get the primitive cohomology, and there the polarization is canonical because it's given by cup product.
But
then,
only in the middle degree, no?
If I'm in the middle degree, if I'm in lower middle degrees and I have the left shot decomposition, that will give me canonical polarization on all pieces.
But still it moves when you move the left shot, the ample class.
Yeah, so I would have to take a relative polarization of the family.
Thank you.
I just wanted to make the remark because it will be.
Yeah, of course, this is related to what Javier will talk about.
Yeah, maybe it's useful to understand Geordie's question, and it will also be useful for my course. So the endomorphisms of the elliptic curve are the Hodge classes in V tensor V dual. So
yeah, so I should have said that here, if you have your elliptic curve E tau, actually the Hodge tensors. So I remind you that the Mumford group is entirely described by Hodge tensors in V tensor something tensor V dual tensor something. But for elliptic curves, you are lucky because it's entirely described in the endomorphism. So you just have to look at the endomorphism of this elliptic curve. So in terms of Hodge structures, this is V tensor V dual. There are no higher tensor to consider actually. And now you want to take the endomorphism as Hodge structures. So here it just as the module. Now as Hodge structure, what happens is that you have exceptional, you have only 2 possible cases. The joint case will be Z. And otherwise, you just, well, I would take of a Q coefficient, or maybe, yeah, you get an order. Otherwise, in Q of tau, if, so this is E tau, if tau is imaginary quadratic. Okay, and so this means that the Mumford group that you get, so G E tau, is restriction of scalars of Q of tau to Q of GM, if tau is imaginary quadratic. And this is GL2 otherwise. So you get GL2 and otherwise you get a torus. Okay. And so these are how these imaginary quadratic points get into the picture. Should have been, I'm short on time, so I was kind of fast. Okay. More questions now.
Could you give some kind of indication of why the Mumford-Tate groups are the same on the generic fiber, or would this be too much to ask?
Well, Okay, so let me give, no, I will not give the precise proof, but let's say you believe in the Hodge conjecture. If you believe in the Hodge conjecture, each Hodge class should come from an algebraic cycle. But now, if you think this way, you see that algebraic cycles have the properties that they deform into family because of the existence of Hilbert schemes. Okay, and so this means that if you have a Hodge class in some fiber, and you look the fiber around where it still exists, then if you believe in the Hodge conjecture, not only it will appear on some algebraic subspace of your original space. So outside of this algebraic subspace, that class will not exist. And so you see that actually this Hodge locus, if you believe in Hodge conjecture, is countable union of algebraic subsets. So I will come to that. It was planned to be done today, but okay. I was just too slow. Okay. I see. That's good. There are many questions.
Can you explain more about the level? Suppose we have like a geometric situation.
Okay, so the first invariant of Hodge structure, you can think this is the weight. So the higher the weight, the more complicated it is. But you see that the weight is actually not the right invariant if you think in terms of moduli spaces. For instance, if you take families of K3 surfaces, so these are surfaces you're interested in the middle cohomology. So this is the cohomology in degree 2, and so the weight should be 2. But then if you look at what happens, actually, what happens is that it's not really true because the moduli space really looks like the moduli space of Hodge structure of weight 1. And the reason is that actually the Hodge structure that is important is not the Hodge structure you started with, but really the Hodge structure on the Lie algebra of the German-Conforti group. So this is why this is very useful to think in terms of Hodge theory. Then the fact that the period map for K3 surfaces takes value in what I will define tomorrow as being a Shimura variety, which basically parameterizes motifs of abelian type, so basically families of abelian varieties. It's no surprise. It's obvious from the point of view of group theory, because on the Lie algebra, you really get a Hodge structure of level 1. So this is always weight 0, but what is important is the depth of the Hodge filtration on this weight 0 Hodge structure. This is really what controls the Hodge structure, not the weight of the original one, which by accident, you see, I mean, if I take something of weight 1 and then I take the second symmetric power, this is weight 2, but actually, originally, this is really weight 1, not weight 2. And so if you look at K3 surface, the constructions that as Kugasatake, what's the name? Yes, Kugasatake, that associate to it an abelian variety, and that tells you that basically you recover your weight 2 Hodge structure of your K3 through the this big weight 1 abelian variety. Okay, this is a nice geometric construction, but from the point of view of moduli, this is obvious because the right invariant, so it's a finer invariant, so this level is always smaller than the original weight. But for instance, for K3 surface, this is really 1 and not 2.
Okay, so we can start. And this is Geordie Williamson from the University of Sydney, and is going to talk about Hodge theory just beyond geometry. Thank you.
Thank you very much. Also, thank you very much to the organizers for inviting me. I haven't written on a board since about 2019. Hopefully, I still remember how to. Okay, so what I'm talking about is Hodge theory just beyond geometry. So this is this kind of amazing world which has emerged over the last 30 or 40 years of Hodge theoretic ideas influencing representation theory and combinatorics. So what's going on here? So this is the setting. So as Bruno explained, if we have X smooth and projective, we can associate to it its cohomology. Let's say with rational coefficients. So this is a graded algebra. It has a Hodge structure. So when we tensor with C, this has a Hodge decomposition. Moreover, this graded algebra satisfies remarkable properties. So the Hard-Lefschetz theorem. Which I'll go over. And the Hodge-Riemann relations. So you have this incredibly rich structure on the cohomology of a complex algebraic variety. So smooth projective over C. Now, what's kind of happened in a number of different situations. So what this course is about is the fact that sometimes, so this is a slogan, sometimes the cohomology ring kind of exists, but X does not. It's kind of a remarkable state of affairs. So there's now about 4 different worlds in which, generally starting from some problem in combinatorics, we can cook up some vector space. And this has all of this remarkable structure, and this structure proves very deep conjectures that have been around for 40 years, 50 years. And so it's this kind of amazing fact that we have this thing and it looks like it should be the cohomology of something, but that something does not exist. And there's situations in which you suspect it doesn't exist, but there's also situations in which it provably does not exist. So examples is McMullen's conjecture. On face numbers of polytopes. So this answers the very basic question of, I have a polytope, how many faces of various dimensions can it have? So this is a very difficult question. This answers it in the case of simplicial polytopes. Another example is Kazhdan-Lustig positivity. So this is a conjecture from 1979, which was proved by Ben Elias and I in about 2012 or something. And the same ideas. So again, this follows from the existence of such a package. And C is several conjectures in matroid theory and in incident structures. Okay, so for example, imagine that I give you 400 points in R7. I can ask how many, so there's 400 points. How many lines are there? How many planes are there? How many free subspaces are there? So this is an example of a combinatorial count that's very interesting. And there's very subtle conjectures about these counts, which are resolved by producing something, producing a cohomology ring. And this is the work of Juni Ha and his collaborators, and he recently got the Fields Medal for this stuff. Okay, so basically all of these subjects are totally remarkable, and I could spend the whole lecture series on any of them, but I kind of, my interpretation of you as an audience is that you really like Hodge theory, but you're maybe not so interested in Kazhdan-Lustig polynomials or the specificities of polytopes or, you know, certain arbitrary counts of matroids or something like this. So there's, you know, there's people in the world that find each of these subjects very fascinating in their own right, but I'm assuming that you are not such people. perhaps. And I'm assuming that you would like to see the kind of general structures that exist here. Okay. So today is the aperitivo. And so this would be an epsilon today. So I just want to explain a simple example of this that I find nonetheless remarkable. So you can see the first example of H star existing whilst X does not. And then this will be lectures 2 and 3. Because in my opinion, this is the simplest place where you see these ideas clearly. And then this is lecture 4. Because so there's something in this, so it's kind of a remarkable situation. So firstly, we had hard Lefschetz in the algebraic world, in the complex geometric world. And then we had this world around convex polytopes. And I think at that stage, people were unsure what was going on. And then this happened. And I remember there was like many people asking like, what is the kind of overarching structure for this theory? And I think we still don't know, but there's this recent work of Juni Hart and Peter Brendan on these things called Lorentzian polynomials, which seems like a remarkable unifying framework, and that will be the last lecture. But I'm not an expert on Lorentzian polynomials. Everything that I'll be explaining, I've kind of learned in the last few days, basically. Okay, aperitivo. The other thing that I should emphasize is that this is a summer school. Please ask questions. And I feel that you have to get your hands dirty with something if you're going to understand. So, you know, choose Bruno's course or choose Javi's course and try to do exercises. You don't learn by just listening to lectures, in my opinion. Yeah. So if you actually want to learn, like choose something that's interesting to you and try to like annoy us with questions, etc. And I'm just speaking for me, but I would be delighted to be annoyed with questions. Okay. So aperitivo, the flag variety. Is that the correct spelling of aperitivo? Good. It's very important. So we start with the flag variety. So this is GLNC modulo B, which is the upper triangular matrices. So the Borel subgroup of upper triangular matrices. And this is isomorphic to the space of complete flags such that the variety of complete flags okay, so for n equals 1, I get a point, and n equals 2, I get lines in a two-dimensional space. So this is P1 of C, and then I get something for all n. And this is a smooth projective variety. Okay, it's smooth because it has a transitive action of this thing. And you can view it as, see it as a projective variety, for example, by embedding it inside a product of Grassmannians, which you probably learnt already are projective varieties. And its dimension is n choose 2. Its complex dimension is n choose 2, and I'm going to denote this quantity by d. So there's a beautiful description of the cohomology ring called the Borel isomorphism. Which says that the cohomology, I'll call this X. This is the flag variety. The cohomology of X. I forgot an important remark. Is that in A, B, and C, only Hodge type PP occurs. Okay, so Hodge theory is an incredibly rich subject, and a lot of its richness comes from the fact that you can have many different Hodge types showing up in a single cohomology group. But in this combinatorial world, it's like we're in the world where everything is generated by algebraic cycles. All the cohomology comes from Hodge classes. And so this leads to a massive simplification. Okay? And for that reason, I'm just going to write the cohomology is always the cohomology with coefficients in R. Okay. So to simplify my life, whenever I take cohomology, it'll be cohomology with real coefficients. So the Borel isomorphism says that the cohomology of X is canonically isomorphic to C, which is the coinvariant ring, which is the quotient of a polynomial ring in X1 up to Xn by the elementary, by basically the ideal generated by symmetric functions of positive degree, and symmetric functions are generated by the elementary symmetric function. So this is the ith elementary symmetric function. So E1 is X1, Xn, E2 is X1, X2 plus X1, X3. Okay, so an example, maybe this is an exercise, is that for n equals 2, this is spanned by 1 and x. I should have said that the degree of xi equals 2. And also, if you like this kind of world, it's very nice to convince yourself that this is true. So these xi's are Chern classes of certain very natural line bundles on the flag variety, but I won't go into detail about why this is true. I'm just saying this is a fact. So for n equals 2, this is spanned by 1 and x. For n equals 3, it's spanned by x1 squared x2 x1 squared x1 x2 x1 plus x2 x1 and 1. Okay, so the Betti numbers here are 1, 0, 2, 0, 2, 0, 1. Okay, so it's some fun commutative algebra to do these little exercises. And now I just want to, so if you think about kind of, so what am I kind of trying to say here? So this belongs to the world of algebraic geometry. And this belongs to the world of algebra. Yeah. So, you know, if I can explain to a second or a third year student what this is, whereas this takes a hell of a lot more. And so now we can say, okay, we have these deep theorems here about this object. What do they mean in algebra, and can we prove them? Interesting challenge. Remember, please ask questions. Okay, so theorem, and I'll state the kind of geometric fact together with the algebraic incarnation. So A is the fundamental class. So C to the 2D, So I've told you that D is the complex dimension of the flag variety, hence 2D is the real dimension, and that's where I expect my cohomology to stop. Is spanned by x1 to the n minus 1, x2 to the n minus 2, down to x minus n minus 2. Okay. And so we can define a kind of trace map on C to the 2D is isomorphic to R, sending this class just evaluating at 1. So that's the fundamental class. The second statement is Poincare duality. So let's call this 1, 2. Duality, which is that I can consider the pairing from C to the D minus I. So D is exactly the middle degree of my cohomology. So I expect Poincare duality to give me a symmetry about the middle degree, which sends AB to the integral over AB dot B. This is a non-degenerate pairing. Okay. So this is our algebraic incarnation of Poincare duality. 3 is Hodge-Lefschetz. So I start at n minus 1, go n minus 2, and so, you know, it's n. So the coefficient of xi is n minus I. So the coefficient of xn is n minus n, which is 0. Thank you. So Hodge-Lefschetz is if we take, so this is the analog of being an ample class. So the sum of lambda I xi such that lambda 1 is bigger than lambda 2 is bigger than lambda n. So this is the analog of an ample class. What we can do is consider the multiplication map by omega to the I from C to the D minus I, and this takes us to C to the D plus I. Multiplication. And the statement is that this is an isomorphism. Okay. Not obvious, but true. I mean, I haven't told you what that isomorphism is. If I told you what that isomorphism is and you unpacked a little bit, it would become obvious that this is the analog of. No. Yeah, and I should say, like, yeah, maybe another fact is like, this is not just ample class in inverted commas. Like, once I tell you what that isomorphism is, it is literally the ample classes, yeah? Or like belonging to the cone of ample classes. So this is an isomorphism. So notice, yeah, so I would strongly recommend if you're kind of interested in this world, at some point you need to spend an enormous amount of time like thinking about hard Lefschetz Poincare duality and how they kind of play with each other. But just notice the following kind of funny thing, which is that here we have two vector spaces in duality. So d minus I and d plus I, one is the dual of the other. Whereas once I've chosen this omega, now they're not in duality anymore, they're the same. And so this means that I get a form on either of these spaces. So now I don't just have a raw vector space, I have a raw vector space with a form. Huh? And for, thank you. I really appreciate, thank you very much for any comments like this. It'll make the lectures much more accurate. Hodge Riemann relations. So this is the statement. So we define P to the d minus I to be the kernel of going one more than hard Lefschetz tells us to go. So we go from C to the d minus I. If we multiply by omega to the I, we land in C to the d plus I. But now we multiply one more time. So that's I plus 1, and we go to d to the I plus 2. And this is what we would call primitive classes. And then the statement is that the restriction of the form that I was talking about before, so this is by combining Poincare duality with hard Lefschetz, the integral over a dot b dot omega I on c to the d minus I is, and now you get this inevitable trickiness of signs that already showed up in Bruno's talk. You cannot escape the trickiness of signs. They're there, like there's a really fundamental reason that they're there. Very important. So it's not just something you can kind of get rid of by renormalizing or something. D minus I, definite. Okay. So I really should spend more time on this if you're not familiar with it, but I'll just kind of draw the following picture. So imagine that our cohomology ring looks like, so it's only an even degree. So this is a picture of the cohomology ring. And now we have this Lefschetz operator, which goes up like this. And you may or may not know that being a Lefschetz operator is equivalent to there existing a kind of map back down the other way, satisfying the SL2 relations. Okay. And so I can split this up into irreducible representations of SL2. So if this is nonsensical, then just ignore me. That's fine. Okay. And then I get these primitive classes. So what would be the primitive classes here? It's the stuff that goes to 0 when I go one more than the Lefschetz symmetry. So I go up here, and so these are my primitive classes. Here I go, this would be my Lefschetz, one more. So this would be a primitive class. This would be a primitive class. And then if I start from the bottom, maybe am I allowed to ask a question of the audience? So what happens if I take my ample class, cup it up to the very top, and then integrate over it? What's that quantity? The volume, yeah, or another word in algebraic geometry. The degree, yeah. So that says that the Lefschetz form here is positive definite. Okay, the degree of an algebraic variety cannot be negative. Yep. So this form is positive definite. Here it's negative definite, and here it's positive definite again. Okay, so another way of saying the Hodge-Riemann relations are that I can tell you the signatures. Yeah, so the Hodge-Riemann relations, when I'm in this funny PP world where all classes are PP, the Hodge-Riemann relations are the statement that I can tell you the signature of these Lefschetz forms just by looking at the Betti numbers. So they alternate in a very prescribed way. Johan. The restriction of, oh yeah, thank you. Johan definitely already earned a copy. Okay, so this is a subspace. This is what Johan is saying. This is a subspace inside CD minus I. Restriction to that is definite of a fixed sign which alternates as I go up. Okay. Yeah, and just, I don't want to sound like a broken record, but this really takes some time to digest, this structure. It's a very useful structure. So if you haven't seen it before and you're interested in the subject, it's really worth time thinking just about that board, what it means. Okay, and all this kind of polarization business and stuff becomes okay, so what I've done is I've taken deep statements in Hodge theory and translated them into a statement about a ring that I can write down explicitly. And one could ask, can we prove these statements algebraically? The natural question. So one is basically an exercise, really not difficult. Two is not too bad once you know a tiny little bit of theory. I know no simple algebraic proof of 3 or 4. Okay. So I do know an algebraic argument, but it is very, very far from simple. So now there's a very natural generalization of this story. So we take V over R, a finite dimensional vector space. And W acting on V, a reflection group. Okay. So this means generated, i.e. generated by reflections, i.e. elements of order 2 that fix a hyperplane. Okay, so for example, the symmetric group acting on R to the n via permutations of coordinates would be an example. So we denote by R the polynomial functions on V with equals 2. And we set D to be the number of reflections in W. Okay, so if I was in the symmetric group case and I was just taking this permutation, like via permutation of coordinates, I would exactly be in the situation up here. So this would be a polynomial ring in n variables. And D would again be the number of reflections in W, which is the number of 2 subsets of 1 up to n, which is n choose 2. And then theorem of Elias and myself from around about 2012. So this is a very special case of a much bigger theorem. is that 1, 2, 3, and 4 hold for C, W, which is the quotient of the polynomial ring. So this is the functions on V, modulo the ideal generated by invariant symmetric elements of positive degree. Okay, so remark. So most of the time, if I ask you to produce an example of a reflection group acting on a real vector space, a good source of such examples are Weyl groups and their action on the Cartan subalgebra of like the actions coming from, for example, compact Lie groups or reductive groups. Okay. Most of the time, W is a Weyl group. And the Borel isomorphism yields that CW is isomorphic to the cohomology of G mod B. So is the Weyl group of some complex group G. Okay, in which case this follows from Hodge theory. But not always. So it's just a ring. But with a little bit of theory of, so what Coxeter did in the 30s is he said, if I have such a real reflection group, I consider all the hyperplanes which it fixes, and then I fix one of those alcoves, and then this determines for me Coxeter generators of my, so I take my reflection group, I delete all the reflecting hyperplanes, and then I fix a fundamental alcove, and the reflections in the walls of that fundamental alcove give me Coxeter generators, and I can write down a beautiful and simple presentation for my reflection group. And I haven't really explained why, but there's a structure on that ring that depends on this choice. So for example, essentially the decision about how to form this trace, what element to assign a positive value, depends on that choice. And this choice also determines a cone of ample classes. Yeah. And all the same things are true. And did you ask that question? Yeah, yeah. Yeah, and really, really not easy to prove. So just an example of not always, we might take W to be the symmetries of an N. So this doesn't look very regular, but it's meant to be a regular n-gon. And this is a Weyl group if and only if n is 4, 6, 8, or 12, I think. Oh, no, sorry. 3, 4, 6. Yep, so this would be the Weyl group of type A2. This would be the Weyl group of type B2. And this would be the Weyl group of type G2. Another example that we could take is W to be the symmetries of the icosahedron. Okay, so this is a Weyl group of type H3, and it's a Coxeter group of type H3, and it has the following Coxeter diagram. And here the Coxeter diagram is. Okay, and somehow this 5 here prevents this from being a Weyl group. How do you form Poincare duality? So this is a little bit related to the question before. So it's easy to prove that the top class is one-dimensional, and then I have to choose what sign to associate top class. Okay, that's a little bit subtle, but I can explain how to do it. And then once you've made that choice, everything that I said makes sense. So you choose this fundamental alcove. This gives you a notion of ample class. And it also gives you a notion of top class. And then, okay. So now I just want to go over. So, yeah, I think so. The example that I'll give now is like you'll see that it cannot be. Okay, so I just want to go over this this example because I find it like incredibly beautiful. So it's the first example. So I want to finish with the following example, which is W being the symmetries of the pentagon. And for this example, so you can view this as an extended exercise. I just want to sketch what happens here. I'm not going to give all the details. I'll sketch what happens, and if you're interested, this is extended exercise. And see, so I wrote a paper with Ben, a survey paper called KL Conjectures and Shadows of Hodge Theory. And it's in the final section. Okay, so I know, like even to do this example on a computer is rather complicated. Whereas this example of an n-gon you can do totally by hand, and that's what we do in this final section of here. So we want to kind of pretend that this is a Weyl group. So pretend so I hope you've met Cartan matrices, and I hope you've observed that usually their entries are integers. Okay, but we pretend that we have a Cartan matrix where phi is the golden ratio. And the usual formulas give an action of W on the span of alpha 1 and alpha 2. Okay. So I just want to show you what the positive roots look like because it's very beautiful. So the positive roots look like the following. So there should be the vertices of a pentagon, and I'm taking exactly half of them. So I have alpha 1 here, alpha 2 here, and here I get alpha 1 plus phi of alpha 2, phi of alpha 1 plus phi of alpha 2, phi of alpha 1 plus alpha 2. And I mean, it's very fun to just act on this via the formulas that one knows from Lie theory, and to see that one has a perfectly reasonable set of positive roots. So if you add these negatives, they're permuted round by W. And we have, so this is our positive roots. And then we have CW is spanned, has Betti numbers. One, 0, 2, 0, 2, 0. 0, 1. Plus a distinguished basis. So in the theory of reflection groups, this co-invariant algebra, CW, is a very fundamental object of study, and people have very beautiful formulas for its greater dimension in terms of the so-called degrees of the fundamental invariance of W. Okay. So you can derive this formula pretty easily. And also it has a distinguished basis. And now I just want to give you a sense for how ample classes look like when we multiply on this distinguished basis. So I just want to draw a big picture. So this is meant to be so this is meant to be degree degree 0, 2, 4, 6, 8, and 10. Okay, so here I see my Betti numbers 1, 0, 2, 0, 2, 0, 2, 0, 2, 0, 1. And now, in order to explain, so these dots are meant to be my basis of this co-invariant ring. So this is a picture of CW. Now, so for example, this is 1. And up here, this is the product over alpha in phi plus of these positive roots. So this is of degree 2, 4, 6, 8, 10, which is correct. So now, so I wanted to describe what these kind of structure constants are. Whoops. Okay, so if I multiply by, so I hope that that's all clear so I can get rid of this. So what I'm going to do is I'm going to put, so if I take lambda in C2, this is an analog, this is what I'm thinking about as being a Lefschetz operator. The only important quantities are lambda paired with alpha check, alpha 1 check, and lambda paired with alpha 2 check. Oops. Yeah, so I'm not explaining this very well, so I'll just I'll write down the answer and then I'll try to explain the answer. So when I multiply my bottom element by a class in C2, I expect something times this plus something times this. And these things on the arrows are encoding what that something is. And then the ones up here are phi alpha 1 check plus. Basically, I get some analogs of these positive roots from before. Okay, so what this means is that if I take lambda sum, let's say lambda 1 times alpha 1 plus lambda 2 times alpha 2, and I multiply by the class living here, or the class living over here, then in order to work out where it goes to, I should pair alpha 2 check with that quantity. I get a scalar. So I use my Cartan matrix to compute that. I get a scalar, and that's the coefficient here. And I pair this quantity, and that's the coefficient here. Okay. And so the extended exercise, so the exercise is check hard Lefschetz and Hodge Riemann. Relations. Okay. And I promise you that it's quite miraculous what happens. So for example, if you start at the bottom, like let's check the simplest example. So if I imagine that I choose lambda such that lambda pairs with alpha 1 check. So lambda is ample if lambda paired with alpha 1 check is bigger than 0 and lambda paired with alpha 2 check is bigger than or equals 0. And you'll see here that only kind of positive co-roots feature. So what that means is that I get, if I start at the bottom, I'll get two positive numbers. And then I keep going and I get more positive numbers, more positive, and at the end they're positive. So that's the first Hodge Riemann relation. Okay? And the second one is a little bit more subtle. Okay? But I find it absolutely remarkable that kind of, starting from a pentagon, we've produced an object that looks like it's the cohomology of something, but it is not. So for example, this is not definable over Q. This is okay. So it's some, if such an X exists in the world, it's something that cannot produce cohomology groups over Q. It has to produce cohomology groups with this, with the golden ratio adjoined. Only over. Okay. And this is meant to be a toy example of one of these objects that exists just beyond geometry. Okay. So in the next lectures, we'll see examples of this coming from polytopes and from matroids. So if you're interested in kind of this world, I just wanted to mention a kind of open question, which I think is very interesting, but I have no idea what can be said. Okay, so if I take a complex reflection group, one can form the co-invariant algebra, and it appears to satisfy hard left sheds. There's been extensive computations that have shown, I think, in all but a very small number of cases, we know that the co-invariant ring satisfies hard left sheds. But because it's complex, it's now unclear how to formulate the Hodge-Riemann relations, for example. Do there exist some analog of the Hodge-Riemann relations? Is there a Hodge theory for the co-invariant rings of complex reflection groups? I have no idea. Another question is that somehow, so this one can check by hand, but if we were going to do this, for example, for the icosahedron or something, we get this very, very interesting vector space. It's very interesting algebra that appears to satisfy all these very strong properties. But the only proofs that I know go through an enormous amount of kind of combinatorics of Weil groups and Zergel bimodules and Cauchy elliptic polynomials and things like this. And this just seems like totally unnecessary to establish such an innocent fact about a beautiful finite dimensional algebra that I can define in 5 minutes. So thanks. And as I said, tomorrow and the next day is polytopes. And then in the last lecture, I want to do a tiny little bit from matroids and Lorentzian polynomials.
Yep. So thank you. Any questions?
Okay, so I have one question. So you say the abstraction is that this is not definable over Q, but you could imagine that there is some Galois action, and you take all the conjugate under this Galois action, then the total sum will be defined over Q, and this could be the cohomology of some algebraic variety.
Yeah, this is exactly what Williamson said.
Thanks.
Yeah. And I did try to do this a little bit, but I still got stuck. But I'm sure that there's some like beautiful answer, but yeah, I would love to try again to do what you said.
Because I was thinking in dynamical system, it's quite usual that you get some kind of variations of that structure, which are defined over some finite extension of Q actually, and because they are just a piece of the total variation of a Q, and you have all the conjugates that they do not play any role. But
yeah, so another thing that, which I think is very similar to what you're saying, is that Williamson said that it's not unusual that you have some algebraic variety, you have some interesting endomorphism of it, and then on cohomology, it satisfies, for example, the minimal polynomial of the golden ratio. And so you get like a structure over the, yeah. And I would like, so many people would be very happy if someone could explain that. So, you know, if you want to think about this, I would be delighted. Yeah.
Okay, who's next? Yeah.
Yes. So can you explain again how you found lambda 1 and lambda 2 so that lambda is ample?
So maybe I'll just explain in the world of Cox-Eta groups what I do.
Also in this case is okay.
Oh, it's just like literally this condition.
Ah, literally this one. Okay.
The lambda is ample if and only if.
Ah, oh, okay. Sorry.
Sorry, it wasn't clear yet.
Yeah, also, yeah, again about ampleness. So you mentioned that in this complex reflection group story that it satisfies hard left sheds. So I was also wondering, how do you define ample there? Is it that it sort of lies in one of the alcoves with respect that you're choosing, or?
Yes, so there's a funny, so if I just stay in the real setting for a second. So this is, I have this very special cone, which makes sense because I'm over the reals. But the whole thing is W equivariant. And so that what that tells you is that when you move to a different chamber, you mess up the signs, but hard left shed stays true. And the conjecture for a complex reflection group should be for any element whose stabilizer under W. So back in this world, it is a fact that for any element whose stabilizer under W is trivial, it satisfies hard left sheds. Okay? And now that statement generalizes to complex reflection groups. And very often in complex reflection groups, people show there's an open set of things satisfying hard left sheds, but they don't pin it down to say it's exactly the complement of all the reflecting hyperplanes. Yeah. And it really seems to me that we fundamentally don't understand why hard left sheds holds for complex reflection groups.
Thanks.
So if we talk about flag varieties, they are iterated bundles of projective spaces. And here in this case, the Betty numbers also look like P1 bundle over P4. Is there, can you in any sense see the structure here?
Absolutely. So you can, so for example, I can take CW and I can take, view it as a module over C, W, and then invariance for a parabolic subgroup. So this would be the analog of, so here I'd have the cohomology of G mod B, and here I'd have the cohomology of G mod P. Okay, and I have pullback. And that pullback identifies this cohomology with some invariance, partial invariance inside here. And now I can say, oh, this looks, you know, in algebraic geometry, this looks nice, like a nice vibration, and so it satisfies relative hard left sheds. And this also we know is true for these co-invariant rings. So they all fit together and they satisfy relative hard left sheds. All the signs are right. It's really remarkable.
Thank you.
But yeah, somehow like I would love a proof for the co-invariant ring that just uses this structure, and I never found one.
More questions? Okay, then. Thank you very much for the talk. We can start with the last lecture of today from Javier Fresán from École Polytechnique, and he's going to talk about periods, motif Galois groups, and the Kontsevich-Zagier conjecture.
Thank you. Thank you very much for the invitation. I'm really happy to be part of this fantastic team of speakers. So who are also very good friends of mine, and some of them I haven't seen for a while. So the topic of my lectures is periods. So I will try to explain what periods are, why cohomology, and in particular Hodge theory, is useful to study them. I will introduce this Kontsevich-Zagier conjecture, which tries to predict all algebraic relations between periods. And then I'll try to, well, it's a very wild conjecture. We don't know much about it, but there has been some progress in recent years. So I will try to explain some ideas of how to do that. So today I'm going to start with periods. So there's a bit of interaction with the talk by Bruno this morning. So I will first introduce again algebraic rank homology, Betti homology, the comparison isomorphism, and try to sketch the proof of the comparison isomorphism, and to give you some examples of which numbers do you get when you write down the metrics of this comparison isomorphism. Okay, so let's start. This case is going to be a subfield of the complex numbers. So for periods, most of the time you can assume it's just Q, or at least it's reasonable to assume it's inside the algebraic numbers. And X is going to be an algebraic variety over K. And then, as we saw this morning, to such an algebraic variety, we can attach at least two different cohomology theories and a comparison isomorphism between them. So first one is Betti cohomology. So this one is, I'm going to consider it with rational coefficients. So it's just the singular cohomology of the complex points of the variety. So you use your given embedding into C to take the topological space of complex points. And here you have the analytic topology coming from C. And you consider the singular cohomology of this topological space with rational coefficients. And this, as you probably know, is the linear dual of singular homology. Donc, here we have singular homology. Which is the homology of the complex of singular chains. You have a complex where in degree P you have the vector space generated by continuous maps from the standard simplex in R to the P plus 1 to the complex points of your variety. And then there are phase maps. Which are given by taking an alternated sum of the restrictions of this simplex to the different phases of delta P. And then you want to, an element here will be represented by a singular chain with no boundary. So sigma is an element in CP X of C. And the boundary is, well, I guess, N. And then the boundary is equal to 0. And if X is, so you don't need any smoothness assumption for this, it's a purely topological construction. But if X happens to be smooth, so then X of C is a complex manifold, and it's a standard result in algebraic topology. Then you can always represent an element in homology by, so here you are just asking that this is continuous, but it's a standard result that you can represent chains by C infinity maps. So you can represent every class by C infinity map from the simplex to X of C, which means that you can extend it to a C infinity map on a neighborhood. And this will be useful because we are going to integrate differential forms on these maps. So you need some smoothness conditions for the integrals to exist. Okay, so this is Betti cohomology. Then algebraic rank homology. So here I'm going to assume X is smooth. it is not necessary to have the RAM cohomology theory, but it's necessary to have it in the simplest form I'm going to describe. So we also see this this morning. So then you can consider the sheaf of Keller differentials. And the smoothness assumption implies that this is locally free. Of rank the dimension of the variety. And then you form the algebraic rank complex, where here you have the differential. And then you have the exterior powers of omega 1. So omega 2 will be a wedge 2 of omega 1, and so on. Okay, so this differential extends uniquely to a differential on each sheaf of Keller differential in such a way that this forms a complex. And then the RAM cohomology, algebraic rank cohomology, is defined as the hypercohomology of this complex. Okay, so it's well, I didn't say it for Betty cohomology. So this is a finite dimensional vector space over Q. So one way to see that is that the complex points of algebraic varieties have the homotopy type of a CW complex of finite type. So because they can be triangulated. And this is also a finite dimensional vector space over K. So you can either see using the comparison isomorphism with Betty cohomology, or from the algebraic point of view, a bit later, you will see how to prove that it is finite dimensional. And as in the case of every hypercohomology of a complex of sheaves, it is computed by a spectral sequence, where you just consider the cohomology of every term in the complex. So it's a spectral sequence in the first page. Where the differentials are the differentials induced by the one in the rank complex. Here. And this implies, for example, that if X is affine, so these are coherent sheaves, so cohomology vanishes in positive degree. So it means that in this spectral sequence, you just have the row downstairs. So all differentials are 0. I mean, in the second page, they will be 0. And this means that you can, in that case, compute the cohomology just using global differential forms. So in this case, this will be the cohomology of the complex. So global sections everywhere. Okay, so for example, from this, you get that the cohomology vanishes in degree above the dimension. This implies, for example, that Hn, the RAM, is 0 if n is bigger than the dimension. Because this complex just stops at omega to the dimension, which, as we saw in Geordie's talk, for example, is not a property of smooth projective varieties. You expect that this goes up to twice the dimension. Okay. Okay, so that's algebraic rank cohomology. So it was introduced by Grothendieck in a letter to Atiyah and Hodge that was published in 1966. And in that letter, or in the paper, he also proves the comparison isomorphism between these two commodity theories. That says that there exists a functorial isomorphism of complex vector spaces. So from H and the RAM tensor C to Betti homology tensor C, which is given on affine varieties well by what you expect, integrating a differential form on a cycle. So as I explained here, on an affine variety, you can represent everything. So this isomorphism is going to be called comp. So you can represent every cohomology class as the cohomology of a global differential form. And then you need to describe a functional on singular homology with complex values. And this is the one that takes a class in singular homology that you have represented as a smooth chain and computes the integral of omega along sigma. Okay. So the fact that this is well defined, so it doesn't depend on the choice of the representative, follows from a Stokes formula. The Stokes formula says that this doesn't depend on representatives. Okay, so for example, if you change omega by d of something, then when you integrate, you get here you will get the boundary of sigma, which is 0. And same if you change sigma by a boundary. And yeah, so this means that it is well defined. And then functorial means that if you have a map, so a morphism of algebraic varieties, then you get induced pullbacks in cohomology. So this is for the RAM, same for Betti homology. And this pullback here is the transpose of the map you get in singular homology. So here you have the comparison isomorphism. And then functoriality means that this diagram commutes, which concretely, if you write down what it means, is the formula of change of variables for the integrals. So it means if you start with something here, you take the pullback, you integrate on a class, is the same of first integrating on the image of the class. So functoriality, or rather the commutativity of this diagram, means that the integral of pullback of omega on sigma is the same as the integral of omega on f lower star of sigma. Okay. So once we have this, the first tentative definition of what a period is that periods are, so I assume K is contained in the algebraic numbers, and periods are the complex numbers that appear as coefficients of this isomorphism. As coefficients of the comparison isomorphism. Okay, what does it mean? It means a number is a period if you can find some algebraic variety X, some cohomological degree, some the RAM class and some Betty class, such that when you compute the integral, you get this number. Okay. So the restriction that K is inside Q bar is because, of course, the computing the coefficients of the matrix depends on the basis you choose on both sides. And the degree of freedom for choosing the basis is given by K. And if K is the complex number, for example, then every complex number will be a period. So this is not something we want. So this, yes. Sorry, I didn't see you. Yeah, no, it's not true. So it's true for affine varieties, because this argument I explained here that the spectral sequence degenerates. In general, it will be represented, so you will have to cover your variety by a collection of affine open subsets, and then it will be represented by a collection of global classes on each of them that satisfy some properties. Okay, so this is why I just said that this is given on affine varieties by this formula. And then there's a unique way to extend this using homological algebra. Yeah. So another reason for which it is not true is this one. So for example, H2 of P1 is one-dimensional, but you cannot represent the generator by a global differential form. Yeah, thank you. So, and the answer is yes. And this will be important tomorrow or maybe the day after. So there's something called Joannulus trick, which tells you that you can always, you start with any, well, let's say quasi-projective variety X, and you can always find a replacement of this variety, which is it's a fibration on affine spaces, such that the total space is affine and the cohomologies are the same. So the pullback induces an isomorphism. So it is true for periods you can reduce yourself to affine varieties, and then you really have global differential forms as representatives. You can try to do the exercise for P2, for P1 already. It's quite entertaining to find the affine variety. Okay, so that was one comment. Yeah, maybe let me make a few comments, and then I will give you the examples. So first comment is, I said this is a tentative definition. And the reason is that there are some integrals that we will certainly like to include in the class of periods. Typical example is the logarithm of a rational number. So this is the integral from 1 to q of dx over x. And it is not clear. So you see it is the integral of an algebraic differential form on some cycle, but this cycle has a boundary. So this is a path that goes from 1 to q. So this cycle doesn't define a singular homology class. And it is not at all clear that you can maybe find another variety where this number is represented as the integral over a closed chain. Okay, so for this reason, it's not enough to work just with cohomology, so we will need to use relative cohomology, and this is something I will speak about tomorrow. You can imagine that if you if you put something else, which is a subvariety where the boundary of chains can be contained, then you really get all numbers you want. Okay, so yeah, maybe time for the examples. And the first two are going to be very easy, but you'll see. I think this is one of the points of the philosophy of motives, how starting from very simple blocks, you can produce more and more complicated cohomology groups or periods for what matters here. So I'm going to start really with the basics, and then you'll see how they give rise to more sophisticated examples. So first one is algebraic numbers. Okay, so in this case, you take a K, big K. So this is a finite extension of Q, so a number field. And you consider the variety defined over Q, which is the spec of K. Okay, so well, it's a smooth variety of dimension 0. So it means that the round complex it's affine, so you can work with global sections. That means that the round complex is just the functions, and there is only cohomology in degree 0, which is given by K, considered as a Q vector space. Okay, and for example, if you choose a primitive element of the extension, you can describe the basis 1 alpha up to alpha d minus 1, where d is the degree. Okay. So in that case, so what are the complex points? Well, so literally the complex points are the complex embeddings of K. Okay, so this is a finite set consisting of d points. So the Betti homology, it will be in degree 0, and it's just Q to the complex embeddings. Yeah, so you just name them sigma 1 up to sigma d. And then with respect to this basis, the period matrix is well, the sigma i's, sigma j's calculated in the alpha I minus 1. Okay. So in this case, you can see explicitly that this theorem is true, computing the determinant. The determinant is the determinant of a van der Monde matrix. So you see that it is non-zero. And this means that the integration pairing is non-degenerate. And well, one of the reasons I'm giving you this example is that the interesting thing here is that, well, even if you just start with alpha and you want to realize this number as a period, you find a cohomology group that has a dimension bigger than 1. So inside the period matrix, there are many other numbers that, as you see, are exactly the Galois conjugates of your alpha you started with. So here you find the Galois conjugates of alpha. And one of the goals of the theory, that this is what will be achieved using this motivic Galois group, is to do something similar for periods. So we like to have a Galois theory for periods. And well, what you want to try to do is not very mysterious. So if you think the Galois group inside the symmetric group that permutates the roots or the roots of the minimal polynomial of alpha. So here you want to find some group inside. So now this will be linear automorphisms of singular homology in such a way that, well, an element here in the group, so this will act on one of these integrals by the formula. So you consider the integral of omega on G of sigma. Okay, so you would like to try to use this Galois action. So you should think this is going to be some motivic Galois group for the moment as a first approximation, which is true for, or should be true for, smooth projective varieties. You can think that this is the Mumford-Tate group in Bruno's lecture. Okay. My little k here in this example is Q. Yes. Is it okay? Yeah. Yeah. So this is big K, which is the number field, and then in this example, the little k is Q. Sorry. Yeah. So you would like to consider this action, but the problem with this is that well, to know that this action is well defined, you want an action on numbers, and this is just an action on the representation of a number as a period integral. So you will need to know that this action does not depend on how you write down your period as an integral. Okay, so for this, the question that arises is, well, which are all the different representations of a given number as a period? Or maybe say differently, what are all algebraic relations between periods? And if you know the answer to this question, or at least conjecturally, you can, for example, define your group G for this to be true. So you can define G as the group that preserves all these actions. Okay, so this is one of the approaches to construct the motivic Galois group. Okay, so let's do a second example. So this is the number 2 pi I. So in this case, the variety is going to be the affine line over Q minus the origin. So this is a spec of Q xy with the relation xy is equal to 1. And yeah, so maybe we start with the complex point. So the complex point is C star. So the interesting cohomology or homology is in degree 1, and it is generated by this loop around 0. So H1 Betty of X is Q times sigma, this sigma here. And now you can write down the RAM complex. This is the complex of global sections. And you find it is given by Laurent polynomials, and the differential sends a Laurent polynomial to its derivative. Okay, so, well, we are interested in H1. So H1 is the co-kernel of this map. And you see that, well, the only thing you cannot, the only Laurent polynomial that has no algebraic primitive is 1 over x. So all the others are in the image of the differential. So what you find is that this is generated by the class of the x over x. Okay, so this is the co-kernel of the differential. And well, now you need to integrate the x over x on the loop. And this is exactly 2 pi I by Cauchy's formula. Okay, so in this case, you find a 1 by 1 matrix, and the entry of this matrix is 2 pi I. And as you know, 2 pi I is a transcendental number. So this shows in particular that the comparison isomorphism, even in this case where, well, the comparison isomorphism says that the 2 complex vector spaces are isomorphic. So this means that they have the same dimension. They already have the same dimension over Q, of course, is it equal to 1. But this comparison isomorphism given by computing the periods is not defined over Q. So it's something transcendental that in this case contains 2 pi I among the coefficients. And actually, you can prove that there is no functorial comparison isomorphism, which is also compatible with the QNet formula that is defined over Q. You can comparison isomorphism. Is not defined over K, not even Q bar. Okay. And so actually, we will see this later. You can consider the set of all comparison isomorphisms between the complex vector spaces, and which are compatible with this QNet formula. So this has a very nice structure. It will be a torsor under the motivic Galois group. And so here what we have is a complex canonical point of this space. So the situation is a bit like maybe the Galois group of Q bar over Q. So we know that this is a huge group, so it is expected to have every finite group as quotient, for example. But we only know how to write down 2 elements of this group. So the identity and a complex conjugation. So the situation here is very similar. So there are a lot of complex isomorphisms between these vector spaces, but this is somehow the only one you can write down explicitly. Okay. In this example, K is equal to Q. So here, yeah. Okay, so I'm going to give you a third example now that maybe we start seeing like a source of algebraic relations between periods coming from geometry or from cohomology. This is a favorite example of mine. So it's Fermat curves. So we are going to consider the curve inside A2. Well, for the moment Q, but maybe it's better to do it over a cyclotomic field. So it's defined by the affine equation x to the d plus y to the d equals to 1. And we also have the compactification inside the P2, which is the same, but not the homogeneous polynomial. And I want to compute some periods of H1 of this Fermat curve X. And here we are going to start seeing some interesting phenomena that were absent from the talks of Bruno and Geordie, because they were always working with smooth projective varieties, which is that we will potentially get some interesting extensions in the picture. So let me first explain how the cohomology of X and the cohomology of X bar are related to each other. So this is done through something called the Gisin long X sequence. Which in this case is very, very concrete. So maybe I start with homology. So you have H1 of X that goes to H1 of X bar. This map is surjective because you can always take a loop inside the X bar and move it so that it doesn't encounter the missing points. So yeah, I think I should call the complements D. And then here you have H0 of D. So this is just a bunch of points. So here you have the map that takes one of these points. And so the point is missing from X bar. And it maps this point to small loop around the point. Actually, if you take the sum of all these points, so you imagine all these loops, and this will be the boundary of a two chain on X that you can obtain triangulating, and then considering everything except the triangles that are the loops. So this means this map is not injective, and what you find in the kernel is the H2 of X bar. Okay, so this is generated by the fundamental class we saw before, and this map sends the fundamental class to the sum of all points. Okay. So this is for Betty homology, and then in the RAM, so we have somehow dual picture. So we consider forms on X bar. We can restrict them to forms on X. So you can prove that this map is injective. And then if you have a form on X, something you can do is to take the residues along the boundary. So this will give you a map from H1, the RAM of X, to H0 of D. This is the residue map. And then here it's, well, maybe the interesting part. So what you can do here, so here elements are functions that, well, let's say we work over C, they are complex valued functions on D. And so this is a point where it is useful to represent classes using an affine cover. So you can write X bar as the union of X, which is affine, and something else, another affine curve, which is you just pick a point which is not in X and you remove it from X bar. So this will give an affine curve. It's a union of two affines. And then you can, so one of the consequences of Riemann-Roch is that you can find a form omega f. So this is a one form on the intersection on these two. And that has residues with poles along D and P and nowhere else. And the residues on D are prescribed by F. And residues here are given by F. Okay, so such thing always exists. So you need to, one of the reasons to choose an auxiliary point is that such a form exists. And then you map it to the cohomology class 0, 0, omega f, which means if you compute this using checked cohomology, so you need to give a two form on X, a two form on two form here, a two form here, and a one form in intersection, and it is this one here. And is that clear, more or less? Yeah, yeah. I think this works over C at least, and I think you can also do it over K, but maybe you need to be a bit more careful. As let's say we do it over C. Okay, so you have this these two exact sequence, and then you have the comparison isomorphisms everywhere. So you could naively expect that these sequences are compatible with the comparison isomorphism. And then you see that they are not compatible. So what does it mean to be compatible? It means that if you take this class here and you integrate it on the fundamental class, then you should get the same thing as integrating the function on the image of the fundamental class. So integrating a function on points, it means evaluating. So this should be equal to the sum of f at the complex points of D. So now recall that f is the residues of the form. So this is not literally true, but there's the Cauchy's residues formula again that tells you that this is true up to a 2 pi I. So this is Cauchy's formula. So this is one reason to introduce a Tate twist. So if you care about periods or if you care about Hodge structures, the thing you usually find is this with a -1 Tate twist, and same thing here, which means that the description of the spaces are the same, but the comparison isomorphism between the two of them is multiplied by 2 pi I. Okay, so this is and then because of this formula, it becomes compatible with the comparison isomorphism. Okay, so let's use this sequence here, for example, to compute the cohomology. So the dimension of the cohomology. So what is the dimension of H1, the RAM? So it will be the dimension of H1 of the compactification. So this is it's a plane curve. It's smooth of degree D. So this is twice the genius. So it's D-1 times D-2. H0 of D. Yeah. I was thinking of cohomology. Thank you. Yeah. So in cohomology, the arrows go the other way, and then you put a -1. Thank you. Yeah. So you have the dimension here. So this is one dimensional, and then this consists. So D is defined by x to the D plus y to the D equals to 0. So it consists of D points. Okay, so you get a D from here, and then you get a -1 from here. Okay, so in total, the cohomology has dimension D-1 times D-2. Okay, so let's find a basis. So A is the ring of functions. Yes, sure. Oh, sorry. Thank you. So this is D-1 to the square. I factor D-1. Thank you. Yeah, so when you have a presentation of A like this, the module of Kähler differentials is easy to compute. So it's just the free module generated by dx and dy and quotient the derivative of this relation. Okay, and what you observe is that the class dx in omega 1 of A is divisible by y to the D-1. Okay, this is because you can do y to the D-1. You can multiply by y dx minus x dy. Okay. And if you do this, so you will find y to the D, and then y to the D-1 times x. You can use this relation to write it at x to the D. And now this is 1 in A. So you find that this is equal to dx. Okay, so this is a Keller differential, which is a priori not obvious because, well, y has poles. And then you can write down the forms x to the r minus 1, y to the s minus 1 times this differential there. Okay. And here r and s goes from 1 to d minus 1. Okay, so in this way you have as many forms as the dimensions, so it's already a good beginning. And do they form a basis? Yes. And so they form a basis. And one reason to see this is that this curve has a lot of automorphisms, because if you consider roots of unity of order d, you can act by multiplication on the coordinates. Okay, so you have your 2 roots of unity. So if theta is exponential of 2 pi I over d, then you have 2 roots of unity, and then you act by a multiplication on the coordinates x and y. So this will respect the equation. and you can check that these forms are eigenforms for this action, and each of them corresponds to a different character. Okay, so they are linearly independent. Eigenforms for distinct characters. Okay, so maybe then the question you are asking yourselves is why these forms? And one reason is that so if now you consider sigma, which is the path given by, so t goes to dth root of t and dth root of 1 minus t. So you can choose the only positive real dth root. So this path goes into the complex points of the curve, even the real points. And if you consider the integral of this form on sigma, well, you just write down what it is, and then you find that this is 1 over d integral from 0 to 1 of t to the r over d minus 1, 1 minus t s over d minus 1 dt. Okay, so this is this function is known as the beta function. So this is the beta function. And it's also equal to a quotient of values of the gamma function. So this is gamma of r over d, gamma of f over d, gamma of r plus s over d. Okay. So these are the kind of integrals that well, people like me like a lot. And this is the way they appear as periods of algebraic varieties, algebraic curves in this case, except that again, we have the problem that this is not a closed path. Okay, so this is not yet a period in our sense, but in this case, we can use the group action again. So it is possible to close this path using the group action. So instead of sigma, you consider sigma minus 1 theta sigma plus theta theta sigma minus theta 1 sigma. So this is now a closed path, and the integral doesn't change too much. So there is just a a factor in the cyclotomic field that appears when you do that. You can compute, so it's 1 minus theta to the r times 1 minus theta to the s. Okay. And now this kappa really defines a class in H1 Betty of the Fermat curve. Okay, so I said that I was going to show this example to start giving an idea of how geometry and cohomology creates or explains relations between periods. So let's do that. So we have the basis omega r s here. And the natural question is which of them come from the compactification extend to the projected curve. And yeah, so for this is easy to answer. So you take the form and then you write down the coordinates of the points at infinity and you compute the residues. And the answer you will find is that, so this depends on the sum. So if r plus s is smaller than d, then they extend to the compactification and with no poles. So they are really global differential forms on x bar. Okay, and then you count them, and you have d minus 1 times d minus 2 over 2, which is exactly the genus. Okay, so it's in the classical literature, these are called first kind differentials. Then if r plus s is bigger than d, then they still extend to the compactification, and they have poles on the points at infinity, but the residues are 0. So poles with no residue. So these are called second kind differentials in the literature. In the case where r plus s is equal to d, then they have poles with non-zero residues. Okay, so non-zero residues. So these are the ones that do not extend to the compactification. They are sometimes called third kind differentials. Differentials of the third kind. Okay, so there's the idea that something special should happen in this case where r plus s is equal to d. And indeed, this is true, because in this case, so let's look at the integral. No, well, r plus s is equal to d, so this is gamma of 1, which is 1. So in this case, the period is, well, you have this cyclotomic factor here. Let's not worry too much. So you have r over d. So there's no denominator. And then the other one is 1 minus r over d. Okay. So then you can use the classical properties of the gamma function. So there's this thing called a reflection formula that says that gamma of z times gamma of 1 minus z is pi divided by sine of pi times z. And if you do rework a little bit the formula, you see that this means that this is a rational or a cyclotomic multiple of 2 pi I. Okay, so it's certainly belongs to q bar times 2 pi I. So this is a situation where the period is a special value of the beta function. In general, you don't expect that these numbers have nothing to do with 2 pi. So this will be one of the predictions of the motivic Galois theory. But in this particular case of r plus s equals to d, the position of the forms in this cohomology gives or explains that the numbers are multiples of 2 pi I. And this is particularly funny in the case d equals to 2. And I will stop with that. So in the case d equals to 2, what we are doing is considering x squared plus y squared equals to 1. And this looks very similar to GM that we were considering before. But the GM is P1 minus 0 and infinity. And these two varieties are only isomorphic when you extend the scalars to Q of I. They are not isomorphic over Q because one of them has rational points at infinity, the points are I and minus I. And this is exactly explained by this Gisin exact sequence. And what you find is that in this particular case, H1, well, I'm just going to write H1 of X. So it means it's true in the RAM or in Betti cohomology. So this is going to be, so in this case, this is P1, so there is no cohomology. So this is 2 points. You have dimension 2, and this is also dimension 1. So, and usually when you kill this class that it's always there, this is usually called reduced cohomology. And it's reduced cohomology, but do not forget the taste twist. Okay. So you have an isomorphism of, well, later we will say an isomorphism of motives. So for the moment, it's an isomorphism of cohomology theory is compatible with the comparison isomorphism and so on. And this explains that, so in this case, the period you are computing, okay, you can do it like this if you want. So if you do it like this, it will be pi over 2. But this depends on basis, so it doesn't matter too much. So it's the Q line generated by pi. Okay. So here you have the 2 pi I. And here, so D is the points I and minus I. So this is the Q line generated by I. Okay. And what you find is that, well, 2 pi I times I, when you consider the Q line, is the Q line generated by pi. So even such a stupid simple relation between two periods, so the first example algebraic numbers and the second example 2 pi I, they combine and they are explained by cohomological identity that comes from this Gisin long exact sequence. Okay, so that's it for today. Thank you.
Thank you very much. Any questions? Well, okay then. I think we are done for today. Thank you very much,
Thank you.
everyone.